Greetings from Istanbul Technical University. I'm Burak, the team leader of i2 Rover team, and I will present you new generation rover, i2 AXA Rover. i2 Rover team is a project team established in 2016 by students studying at different engineering, science and architecture faculties who are interested in space studies and rover science. Our team consists of 5 sub-teams: mechanics, electronics, software, organization and science. As a result of coordinated work of 48 members of the sub-teams, i2 Rover team creates a school in a field of engineering. The European Rover Challenge is a teacher who will open our dreams with all our sides and make us better than we are. And it is a fire that unleashes our passion and ideas for the future. For this reason, participating in the European Rover Challenge represents a great opportunity to do what we do in a better version of ourselves.
For overcoming any type of obstacle and adapting to challenging terrain, ERC suspension mechanism with a differential bar is used in the present Rover. Wheels are custom designed to damp vibration and improve field performance. For safety, high wear-resistant TPU is used for manufacturing the wheels. The motors are positioned in the wheels' aluminum hubs to protect them from environmental factors. An emergency stop button that cuts the power which supplies the motors is placed somewhere visible and easily accessible in order to be quickly pushed in case of unexpected situations.
The 6 degrees of freedom robotic arm consists of 3 different motion systems. A belt and pulley system is used to create a quiet working and lightweight first axis. The second and third axes are run using 2 linear actuators which provide high joint strength and help safely lock the joints in place when the motors are not powered due to their non-back drivability. Cycloid gears used in the last 3 axes help achieve compactness, high precision and zero backlash. All the joints are driven with L-shaped DC motors which help self-lock.
The force load container is designed to carry probes steadily in the probing task. For safety, the covers prevent probes from falling. To lighten the rover, PLA has been used to manufacture the system. The container is placed at a 45-degree angle to the rear of the rover so that the robotic arm can take the probes comfortably.
The control of the rover is done with the Hero development board and STM32 microcontrollers. For the drive system and the robotic arm, Talon SRX motor drivers have been utilized with the CAN bus protocol. Also, the development process of the custom motor drivers and the main board is ongoing. Magnetic encoders are utilized for the velocity for the drive system and the position data for the robotic arm. With the help of the data obtained from the encoders, PID controller is realized to ensure the smooth trajectory of the robotic arm and increase robustness of the drive system. A power distribution board designed to keep the power lines as organized as possible. The board will be ready for deployment in early August. Additionally, an energy monitoring board is in the design process to track the energy expended along the operation.
The design of the power and internal communication systems are made to ensure the safety and robustness of the rover. The cables are organized to reduce the possible noises and short circuit risk to bare minimum. In order to reduce the effect of the possible damage or malfunction of the various electronic components, 2 fuses were added for the 20-volt and 24-volt splitter in addition to emergency stop button. The internal communication system is established by using serial communication. The base station and the rover communications with ubiquitous M2 ballast over 2.4 GHz frequency band and the 6 dBi omnidirectional antennas.
As software team, we have achieved semi-autonomous performance of competition tasks. Fully autonomous operations will be ready in the remaining time. State machine algorithm will be used in order to control our autonomous systems. Activity indicator is used to show our rover is ready to perform an action in a range of 10 meters. All of the lights available on the activity indicator will be lit at least 5 seconds before any operation. Additionally, orange light will be lit during teleoperation and red light will be lit during autonomous mode continuously.
In navigation tasks, path planning and obstacle avoidance is obtained by the move-based algorithm. IMU, wheel encoders, extended Kalman filter and SLAM are used to maintain the localization of the rover. Point cloud data from depth cameras are connected simultaneously to create a local map, which will inform the rover about the obstacles, landmarks and probes. RealSense D435 cameras are used to obtain the desired map. Alvar ROS package is used for air tag detection. Various OpenCV algorithms are chosen to improve the perception.
Probing task consists of 2 parts: kinematics and perception. After the rover reaches desired coordinates in navigation task, the robotic arm will follow the predefined poses to grab and plant the probe autonomously. Teleoperation mode is available as a backup plan for unexpected situations. The kinematic tests of the robotic arm are being made both in simulation and real world. YOLO algorithm is chosen to detect probes after the rover returns back to deployment locations. Thanks to its perception capabilities, real-sense depth camera is used to localize probes and facilitate the approach.
In order to satisfy maintenance tasks, YOLO is chosen for object detection, MOVEit is determined for kinematics. Each panel element is trained for various angles and brightnesses. Depth camera is used to obtain the locations of elements. Depth camera is positioned in a convenient way to accomplish each panel objectives. Derived positions are evaluated in MOVEit to find an inverse kinematic solution. Different manipulation and approach functions are being prepared for distinct scenarios. Our systems are being tested with task invitations for overcome maintenance tests in a competition.
As a science team, we examined geomorphological, chemical, physical and biological features of the Mars yard in detail for this competition. We examined the existing mountains, extinct volcanoes, water beds pouring into the ancient ocean, pyroclastic flows and ice lava interactions in the region between the given coordinates.
As a result of the investigations we made with the geology students in our team, we chose the most suitable location for the rover vehicle to land in, taking into account the areas where the vehicle will be examined in order to determine the correctness of our hypothesis. It was known that there could be alluvial deposits in the waterbed flowing into the ocean and that these alluviums could contain fossils, which was the evidence confirming our hypothesis.
We knew beforehand that we could determine whether there was life that existed and die out at the same time by looking at the rock types and the cracks in the rocks and examining the amount of gases in the atmosphere.
We prepared our hypothesis in line with this information by using camera and artificial intelligence systems. The geological forms and specific rocks on the surface of Mars will be displayed, and the type of rocks in the environment will be determined.
The formation of rocks that exist where ice lava interaction and pyroclastic flow obtained will allow us to have an idea of what environment was like before.
The obtained findings are crucially important for proving our hypothesis. Finding life and detecting a geological anomaly may radically change our perspective on Mars and further accelerate our plans to go to Mars.